Welcome to our Chemistry of Life lecture. We will be discussing the building blocks of matter, specifically elements or atoms and their very basic principles. We will talk about the periodic table. We will talk about elements and compounds, how we go from a single atom to a molecule, so levels of organization. We will talk about electron configurations and how that's going to lead to different forms of chemical bonds. Essentially 3 kinds of chemical bonds. From there, we will talk about the macromolecules of life. One of the most fundamental things in the biological sciences is that when you're talking about an organism, you are talking about something made out of 4 organic molecules: carbohydrates, proteins, lipids, and nucleic acids. And nucleic acids are actually the basis for ATP as well. If you start reading into the cell and how the cell works, ATP is an important molecule. So we will talk about the nature of those molecules, how they are going to interact. We're going to talk about their basic building blocks and how they go from basic building blocks to complete complex molecules that contribute to components of the cell. And that's going to be a really nice transition from chemistry to cells, to the cellular level of organization, which will be our next lecture after this. Now, if at any point you need something off of the periodic table of the elements, for example, in an exam situation, you will be provided with a periodic table of the elements. The important thing about this periodic table right here is that you are able to fundamentally read what information is being presented to you. So first of all, you need to know be able to know which one is the atomic number and what that means. So the atomic number is the one on top. And the atomic number refers specifically to the number of protons found in the nucleus of the atom. Now again, I will be covering exactly what protons, neutrons, and electrons are in just a moment. So again, atomic number is just about the number of protons, whereas the atomic mass number, located below the symbol of the element, is going to be reflective of its mass, which is actually going to be a sum of protons and neutrons, because both protons and neutrons have a distinct measurable mass, whereas electrons are pretty lightweight. So they're really not going to have a mass that registers for the purposes of our atomic mass number, or atomic mass. The other thing that you can get from the periodic table of the elements that's going to come back many, many times throughout your biological sciences career and chemistry career is how these groups work together, how these columns work together. The way it's arranged is that things with similar properties will be found in the same columns. So stuff over here, all of this column, they all have similar properties. And this over here, group number 8, also has very similar properties, and these tend to be very, very stable. These are going to have a filled valence shell, which we'll talk about in just a moment. Whereas if you are just one over in this direction, these tend to be just a little bit negative. Whereas if you're over in this direction, these tend to be just a little bit positive. And when they're just a little bit off from that filled valence shell, that's where a lot of our really interesting reactions are going to take place. So pay special attention to like the fact that sodium and potassium are over here, and then like chlorine is over here. That's pretty important to us. That's going to come back. Some other important ions, magnesium, calcium is going to come back in your biological sciences education, and this is 2 over. These are 2 plus. And those, I think, we'll see carbon a lot. We'll see oxygen a lot. Carbon, we'll find, is going to like to make 4 bonds. That'll come back for you later. And oxygen's pretty negative. That'll come back later. So I think that's actually enough of that. You actually are not going to see a specific periodic table explanation in your textbook. I just read it because it's been a while since I did anything involving chemistry. So it's not necessarily there. This is similar to a chart in your textbook. It's from a slightly older textbook, I think, that Northwestern has stopped using. I do have a cheat sheet right here, just so that you know what I'm looking at right now. So now, this right here is the percent of human weight made up by that element. So if you're going by percent of human weight, oxygen is by far the most common element found in the human body. Now, that's if you're going by weight. If you're going by number of atoms, it's actually hydrogen. Hydrogen is actually, if you count by atoms, not by mass. Remember, hydrogen is a lot smaller than oxygen. So you're going to get a lot of hydrogen in a pile before you reach the same mass as one oxygen. If you're actually just going by a percentage of atoms in the human body, then hydrogen makes up 63% of the atoms in your body. Again, by number, not by mass. It doesn't have a lot of mass, so it only makes up 10% by mass. So if you're wondering why there's a discrepancy between those numbers, it's because those are measuring different things in different columns. This is actually found in the third column in your textbook for a very similar chart. Either way, you still have the four most prevalent ions as oxygen, carbon, hydrogen, and coming in a distant fourth is nitrogen. So you'll deal with those elements a lot in our organic molecules. All of our proteins, our lipids, our carbohydrates, our nucleic acids, they're pretty much going to have those four things. In fact, the two most fundamental amongst those are hydrogen and carbon. The reason oxygen is so prevalent is because all of the water in your body, H2O. And of course, you're breathing a lot of it too. So I've already started using phrases like protons and neutrons, so let's just take a step back or two and go back to exactly what is happening in an individual atom. Now, an atom is the smallest unit of anything. So an atom of an element is the smallest unit you can have of that element that retains properties of that element. So you can have elemental hydrogen, that could be one atom of hydrogen, it could be 10 atoms of hydrogen. As long as there's nothing else in that mix there, then you have the same properties, whether it's 1 or 10. So an atom is just one of hydrogen, or one of, let's see, that looks like carbon right there. Maybe that. Let's assume 6 of each, and let's say that's carbon. So what I'm saying here is that the structure of an atom is that it's going to have a nucleus and an electron cloud surrounding that nucleus. The nucleus is going to be a very, very small area, and the things inside of the nucleus are protons and neutrons. So your protons are going to have a positive charge. Your neutrons are going to have no charge. Beyond the nucleus, there's going to be a sort of cloud of electrons. And if you're playing your cards right with your atom, if your atom is in its pure form, then you're going to have the same number of electrons as you have protons. Yes. Now, you're always going to have the same number of protons versus electrons. If you're oversimplifying it, you can actually change the number of electrons you have. If you change the number of electrons, we call it an ion. You can also change the number of neutrons you have. When you do that, we call it an isotope. So we will rebound back to the concepts of ions and isotopes in just a minute, but I wanted to give you some sense that as clear-cut as this definition is right here, we are going to switch it up in just a minute. So again, the nucleus occupies a very, very small area, only containing neutrons and protons. The electron cloud, the electrons themselves are tiny. They are minuscule, so minuscule we don't even consider their mass at all, but they're moving very, very fast. And so they're moving very, very fast, and I like that my hand is blurring right now because that indicates that we don't actually necessarily know where this electron is within this cloud at any given moment. In fact, if you're into physics, once we figure out the location of an electron, we've lost the speed. Once we figure out the speed, we've lost the location. It's actually kind of a big deal in physics that this cloud of probability that we've defined for the location of our electrons it's a cloud of probability. We don't actually know where that electron is in this cloud at any given moment. We know that the electrons are orbiting around the protons. That negativity is bound into a sort of orbit to the protons. At least that's how it's supposed to work. Now you do have these shells, these orbitals. And your most fundamental and basic elements like hydrogen are going to have one orbital. And then as you get to higher numbers, higher atomic numbers, higher atomic masses, we add on protons and neutrons and electrons. When we get to larger atoms, we do add a second and then later a third and then on and on shell. And the outermost shell that exists for whatever atom you're looking at is called a valence shell. Now, if you're just hydrogen or helium, then your valence shell can hold 2 electrons max, 2 electrons floating around in a cloud of probability. Once you get beyond 2, we move on to the second orbital, and your valence shell now is going to be happiest at 8. It wants 8. You're either going to lose it and just go back to the lower one, or you're going to gain electrons until you get to 8 electrons. That's where it's going to be happiest, is if there's 2 in the first layer and 8 in the second layer. Happy, happy time. If you can't have 8 in the outermost layer, then the preference is going to be 2, just on the innermost layer and nothing else. Empty valence shell is a possibility there. Now, that outer valence shell at 8 for things like oxygen, carbon, anything over 2 on the as an atomic number, that's going to lead to a lot of really interesting interactions. Now, if it's a stable thing, if it's a noble gas, then it has to enter 8 outer and everybody's happy. Or at least I should say the outer valence shell is always going to have 8. And it's happy, and that makes it non-reactive. So it's actually when we have a number other than 8 in the outer valence shell where things get interesting and bonds can happen, because bonds are going to be based on the activities of these electrons. So again, protons have a positive charge, and they have a mass of 1 atomic mass unit. Neutrons have no charge, they are neutral, and they do have a mass of 1 for our purposes. Electrons have a negative charge, and for our purposes, their mass is negligible. We do not count their mass into our atomic mass number. Again, these two are found in the nucleus. These are found in orbitals and a cloud of probability. Now, I mentioned that it is actually possible to change the number of neutrons. It is also possible to change the number of electrons. So when we change the number of neutrons, we call that an isotope. Because we have changed the number of neutrons, that does mean that an isotope will have a different atomic mass, and that number on the periodic table is going to change by 1. Radioisotopes, meanwhile, are specifically really radioactive, typically very unstable isotopes. They tend to emit energy, including but not limited to radiation. They may emit particles. The thing with radiation is that energy and those particles can mess up your DNA, and they can cause mutations, and we're actually going to use that. We're going to use that in medicine. We're going to use it a lot in nuclear medicine. We're going to use it in chemotherapy and radiation specifically. When we give somebody radiation as a cancer treatment, we do use certain radioisotopes such as cobalt-60 as that in that application. What's happening there is you had a mutation that led to cancer, but the cells were not too mutated that they died. So we're going to go ahead and irradiate those specific cells more until they're so mutated that they die. And I'm not being hyperbolic, I'm not being facetious, I'm being very literal. It's literally what we're doing. We are irradiating them to the point that they can no longer function. And at that point, that means that a tumor can no longer grow. It might shrink the tumor. It's just the most effective way we have for now to target an already mutated cell. It's a little bit weird, frankly. But it is the best we have. It's not a conspiracy to keep the general public sick. There's no secret cure for cancer that researchers have, that rich people get access to, that the general population doesn't have access to. Not that I know of. I'm not a shill for big chemo, but I have heard those conspiracy theories before that there is a cure for cancer. They just don't want us to have it because they want to keep us sick, because that means we're returning patients. I've heard that a lot from students at various places, and as far as I know, that is not the case. Chemo is the best we've got. Radiation is the best we've got so far. And again, radioisotopes are something that we can utilize to improve our outcomes in cancer treatments. Another thing we'll use very specific radioisotopes for is we might use them to tag things. We use them in imaging, not some imaging modalities. So if we want to find a specific chemical atom element in the body, there are radioisotopes that will specifically bind with those. We can tag those radioisotopes with something that will show up on imaging, put it in the body, it goes to the place that has all those molecules we're looking for, and then we can track down that thing in the body. So we actually use radioisotopes quite a bit in medicine. They are important to us. Now, we've gone from atoms. We're about to go up to molecules. We're going to go from molecules to cells. We're going to go from cells to tissues, so on and so forth. If we're going to go from atoms to molecules, we are going to need to synthesize. We're going to take two subunits and we're going to attach them to each other. We're going to make a bond between them. Creating a bond is going to require energy. And energy is the capacity to do work. So we find that once we have made this molecule with two elements that are bound together or more, once we have this substance, that bond now holds energy. So remember our gradient triangle. Our gradient triangle is going to work for us again in understanding how energy does work. It takes energy to make a bond, to go from simple to complex. It takes energy. And once you've gone from simple to complex, let's say two individual atoms, two atoms bound together, when you've gone from simple to complex, you've added energy into this molecule. There is now energy in that bond. Go ahead and show that to you. That little arrow there for that bond. Which means if you ever then go from complex to simple, you are going to release energy. And now there's energy that can go somewhere else. Just like pushing a boulder up a hill takes energy, and allowing a boulder to roll downhill is going to release energy and be able to crush a castle at the bottom of the hill, right? So we can store energy in bonds between different atoms. As we make something go from simple to complex, we are storing energy in those bonds. Now there is something called potential energy, which is stored energy, and there's also kinetic energy, which is movement. Something in movement has energy as well. And we can convert from one to the other. We are going to see this a lot in biological systems. We are going to see bonds that break specifically to release energy, and we're also going to see gradients built to create mechanical energy, and then that as that gradient collapses, that's going to release energy. That's known as kinetic energy. So our cells are going to utilize molecules for both potential energy and for kinetic energy. And it's always going to work based on the same basic principles. Now, electrons have potential energy because of the position, because there's more than one shell, because there's valence shells, different orbitals, and because bonding involves interactions between electrons. So the most common way that we're going to see energy stored is actually going to be related to our adenosine triphosphate molecule. This bond right there. See how many things we built onto this? And each one of these stores energy. This is the highest energy bond here. There's a lot of energy in that bond right there. There's nitrogen right there. say anything about that slide. So the next thing we do is talk about three types of chemical bonds, and we can kind of circle back around to the idea that these chemical bonds can store energy. The main one for energy storage for us is going to be our covalent bond. So our three types of bonds are covalent, ionic, and hydrogen bond, which is actually technically not really a bond as much as it's an attraction. As we move down this list from covalent, that's going to be our strongest. Ionic is going to be moderate, and hydrogen, not really truly being a bond, is going to be fairly weak. So let's talk about the natures of these connections, and let's talk about why covalent is strong, why ionic is moderate, and why hydrogen is going to be so weak. The natural world of biology is going to utilize those properties to make it either easier or harder to build something or break it down. So the properties of these are important to the functioning of some of our physiologic processes. Now I mentioned you can form an ion by either gaining or losing an electron. Electrons are negative. So let's say I've got, one electron in my valence shell right now, and right now the number of electron matches my number of protons. So I'm just a sodium atom right now, but I can lose that electron, which again, you've got this valence shell right here. There's only one electron in it. We want a valence shell with 8 electrons in it, so this one being right here is really unstable. So this one really wants to leave. Then we can just have an empty shell here and a valence shell with 8, and then that's really happy. So here's our sodium atom in its typical state, in its elemental state. And then it's actually happiest if it loses one electron. Losing one electron means you're losing one negative, which means you actually now have one more proton than you have electron, which makes you +1. So one positive symbol ends up attached to this core that is symbolic of sodium. So now you've got 8 electrons in the valence shell, and you're really, really happy, but you have a charge. You have this positive ion charge now. Meanwhile, if you are a chlorine atom, you're going to have 1, 2, 3, 4, 5, 6, 7 electrons in your valence shell, and guess how many you want? 8. So you really, really want to take an electron. And if you do succeed in taking an electron from somewhere, you're very, very happy to have 8 electrons in your valence shell, but now you have one more electron compared to the number of protons, and that means it's electrically negative, 1 negative. So you don't have to write the number 1. The 1 is indicated by the single minus sign. There are other ions. They form basically the same way. They form because they're trying to make that happy valence shell of 8. Now, because sodium specifically likes to end up +1, and chloride specifically likes to end up -1, that means these two are going to really like to interact with each other. It means that sodium can specifically lose an electron to chlorine, so that we have a sodium ion and a chloride ion, and because this electron was specifically given to this chloride, now this is positive and this is negative. Now they have an electrical attraction to each other. So they're not sharing the electron. That electron is over with chloride, but it used to belong to sodium. Once it went over, they became positive and negative, and now, shoop, like any electrical gradient, the positive goes towards the negative, and they tend to align into this salt. Your textbook does not refer to this salt as an ion. It refers to this as an array of ions. Or sorry, it does not refer to this as a molecule just yet. It refers to it as an array of ions. So take that as you will. I think that's an interesting difference in how we're going to categorize these things, because when we have a covalent bond, by contrast, we will start to refer to that as a molecule. So again, a molecule is going to be a bonded arrangement of atoms, whereas this is just an array of ions. So this is a great way to get some salts, ionic bonds. And again, that is a moderate strength bond. It is possible to separate those things. We will see that once you introduce water to the sodium chloride, table salt, it is going to dissociate the sodium and the chloride. They will retain their charges. They will be separated from each other. Let's come back to this concept. So let's go to covalent reactions. Now, a covalent bond is when things have similar electronegativities. Now, in that ionic bond, we had something that ended up positive and something that ended up negative, and the positive attracted the negative. When we have a covalent reaction, we're going to start with two things with similar electronegativities, so two negative things. For example, chlorine and chlorine. So they have similar electronegativities, but we still have an unstable valence shell. We still have an unstable outer shell. And one way to stabilize these outer shells without donating or receiving electrons is to instead share electrons with each other. So if this chlorine shares this electron with this chlorine, and this chlorine shares this electron with this chlorine, these two electrons can occupy both clouds of probability. So they might be over here, they might be over here at any given moment. But for both of these chlorine atoms, they're going to have what they consider to be a filled octet, a filled valence shell. So this makes them very happy. When we draw this bond, by the way, we do illustrate it like this. Cl is the symbol for chlorine, and then this single line right here binds it to another Cl. This single line represents two electrons. So instead of drawing out those two electrons right there, we just draw one single line to represent that they are sharing them. Now, if we were to share 4 electrons between them, we could draw 2 lines across, and that would be a double bond. So water is an example of a biologically significant covalent reaction. So what happened here was you had 2 hydrogen atoms. They have 1 proton and 1 electron each, and that's the standard form of hydrogen as an element. Meanwhile, with oxygen, we do have an unstable valence shell. So 1, 2, 3, 4, 5, 6. If only this had 2 more electrons, it would be so happy, right? Oh my gosh. Now, once again, we can simply share this electron. Oh yeah, and don't forget, with hydrogen, we've got our inner shell only. We only have that first layer shell. And this one wants how many electrons on only that innermost shell? It wants 2. So again, this will be most happy if it can just get this electron over here. And this will be happy if it can just get this electron over here. So what we're going to do is we're going to have a covalent bond between this hydrogen and the oxygen and this hydrogen and the oxygen. We'll have one line connecting these two, one line connecting these two as our chemical symbol, as a symbol for this molecule. But what we're going to find is that now that this has effectively achieved an octet, it's going to be very negative. Our electron cloud is going to want to hang out closer to the oxygen side of this molecule. Whereas the hydrogens with their 2, and again, they don't have as much positivity compared to this. Look at how many 8 protons you get over here. So the electrons really want to go to those 8 protons. Meanwhile, this 1 proton just isn't strong enough to pull the electrons over to it. So relatively, the hydrogens over here are going to be positive, and the oxygen is going to be negative. That means that an H2O molecule is going to be negative over by the oxygen and positive over by the hydrogens on both sides. We are going to have a pull of electrons over to this oxygen much more often than those electrons will be found. Remember, it's a cloud of probability. So a cloud of probability says electrons are out here and only a little bit out here. That's the cloud of probability we're dealing with right now. Now, that's not true for every covalently bonded thing. Some covalently bonded things are going to cause a charge in the electronegativity and make it polar. But some of these are non-polar. So chlorine gas, as far as I can tell, there's not going to be any polarity here. This is a non-polar covalent bond. So just because it's covalent doesn't necessarily mean that it's going to be polar. But compared to our other reactions, it's more likely. So you'd actually have to do the math. You can do the math if you feel like it to figure out which reactions are going to be polar or non-polar. So here's that polarity. So this is from your current textbook. Here's that polarity, and this is showing those electrons really like to hang out closer to the oxygen. If there was no pull between the protons and the electrons, you would expect the electron cloud to be over where this dotted line is. But because there is a pull towards the oxygen, then our new cloud of probability is shifted over towards our oxygen. And this is going to directly relate to how our hydrogen bonds work. Now again, with hydrogen bonds, there's no exchange of electrons, there's no sharing electrons. The electrons aren't moving. The bond here is simply a chemical attraction between a positive hydrogen and a negative something else. So if you're arranged, let's pretend instead of this, let's move this on to a completely different concept. Let's say this positive hydrogen gets near this negative oxygen. Now you have an electrochemical attraction between the positive hydrogen and the negative oxygen. And we do find that water likes to align this way. We find that positive hydrogens like negative oxygens, and as we make water colder and colder, and these molecules slow down, which is what happens when you introduce cold to the substance, these things tend to align. So all of your, let's do it this way, all of your hydrogens are going to point to all of your oxygens until it solidifies into ice, which is highly organized, compared to water, which is highly mobile. So there is quite a bit of hydrogen bonding between water molecules. That increases as it turns into ice. Let's go back just a bit. Hydrogen bonding isn't exclusively occurring in water. It is occurring anywhere that there is a positive hydrogen attracted to any other polar molecule. Now we are partially saying that it is the protons of this hydrogen attracted to the electrons of something in a different molecule. That's what we're saying. This polarity of water is a really important principle in terms of how it's going to behave. Water is really important because it's a universal solvent. It's not on this list, but it should be. Most things, more than half the things in the world, are going to be dissolved when you introduce water to them. The other half will be dissolved when you introduce lipids to them. So because they are polar, because they're liquid at body temperature, and because they are what we call a heat sink, they absorb and hold energy, they help keep the body temperature stable. The body temperature is partially stable because of the presence of water. So it helps regulate body temperature, and then it's also a major solvent. So again, if you introduce sodium chloride to a water solution, The sodium is going to be attracted to the negative oxygen. The chloride is going to be attracted to the positive hydrogen. And you're going to end up breaking that ionic bond with your water. So that's the way in which it's going to act as a biological solvent. It's going to be solvent for anything polar or charged. It's not going to be a solvent for anything that is nonpolar or not charged. So again, water keeps ions in solution. There's your dissociated sodium and chloride separated from each other. It works best in our body if we have free sodium and free chloride. Those two ions pop up a lot in physiology, so it's important that those ions are there, separated. And I think I'm going to go ahead and stop here before we get into acid-base balance and do that as our next topic.